Adesso.
Mi sentite? Are you hear me?
Yes.
Okay.
The
But yes, this is me. But I hear myself from here, it's normal.
No,
No.
but I don't know.
That way.
Do you have the audio off?
Yes.
So
Maybe.
volumezzare.
Okay. Maybe not. No. Okay, perfect. And yes, this is the ELT some months ago. It's in construction, really. The main guidelines are motivation and states of art data. I will talk about the photometric analysis. I did a small spectroscopic analysis, and we will see about the next step. At the beginning of the PhD, basically, I asked myself why I want to study globular clusters, why globular clusters are important in this field. Basically because globular clusters are not only in the center of the galaxies, but we can find globular clusters also in the outskirts, so they are perfect in order to trace the galaxy's properties. Since they are the first stellar objects that formed in the early universe, they are perfect also in order to reconstruct the formation and evolution of the Milky Way in this case, but also of the other galaxies. And probably they are good tracers of past accretion events. What we know about these clusters until 2021, basically we know that there are 170 globular clusters. Mainly they are located in the bulge and in the halo. But if we compare the globular cluster system in the Milky Way with other galaxies, for example, with the Andromeda galaxy, we can see that the number of the Milky Way globular clusters is about 1/2 of the number of the Andromeda globular clusters. But also in the Milky Way, if we compare the number of the open clusters, they are much more higher than the number of the Milky Way globular clusters. So my idea is that the census of the Milky Way globular clusters is incomplete. But maybe we can expect this because there are regions in the Milky Way which is very difficult to study, probably because these clusters are very faint, widespread, and are located in very obscured regions. As you can see there in this extinction map, it's very difficult to study the galactic plane of the Milky Way due to the dust. Also, we know that the history of the Milky Way is an history of accretion. At least we know 7 accretion events: Crater, Elmstream, Sequoia, Gaia Enceladus, Sagittarius, but also we can consider the Magellanic Clouds. And as you can see from this interesting tree diagram, each accretion event lead also a number of globular clusters inside the Milky Way. In the other part, from here also we can see that there are several stellar debris structures, and probably these structures are formed due to the disruption of satellite stellar streams. Probably they are dwarf galaxies or globular clusters. However, especially we can see from this figure, mainly the structure are founded in the galactic halo. We don't know anything about this area because of, again, the dust. And I think that this is due to basically, yes, an effect due to the dust. And probably we can expect that in this part of the galaxy, we can find other past accretion events. And probably they are connected to globular cluster dissolution. So my idea is to search for these new globular cluster candidates, study them using photometry spectroscopy, and also I would like to understand if these new clusters, which are, I will show you, very small, low mass and low metallicity, maybe they are formed ex situ, or maybe they, due to other process, they were disrupted, so they formed in situ. So we don't know anything about the nature of these clusters. And I think that this new object can say something about the formation and evolution of the Milky Way. The data that I used basically are the photometric and spectroscopic one. Starting with the photometric one, I used mainly the VVV because we can cover indeed the bulge and a part of the galactic plane. We can study evolved stars, especially red clump, which are fantastic in order to calculate distances. The red giant stars have their emission peak in the near infrared, and the near infrared is the wavelength of the VVV survey. The near infrared is perfect in order to overcome the problem of the interstellar dust, and as you can see here, we can resolve much more better star by star, better than the two-mass survey, for example. I also use it to mass photometry because the images of the VVV at KS magnitude lesser than 11 are saturated. So in order to reconstruct and in order to have a more complete color magnitude diagram, I use it to mass photometry. I also use it Gaia early data release tree, but also the data release tree in order to use the astrometry and eliminate all nearby stars from the catalog, but of course in order to use the proper motion, which they are perfect in order to separate the star cluster member with the field stars. About the other data that I have, they are coming from iGreens. iGreens is a shell high-resolution spectrograph covering the H and K bands. It was at Gemini South, but now it's come back to McDonald's. It's an high-resolution spectrograph, but it's a super good instrument, I think, because we can get precise radial velocities, but also we can derive different elemental abundances in order indeed to understand the nature of these new globular cluster candidates. I will start from the photometric analysis. The thing that I would like that you keep in mind is the fact that the Milky Way, the census of the Milky Way, and also the Sagittarius globular cluster systems is still work in progress. There are several papers in the literature. I will show mine. The main difficulties that I met during this work are differential reddening and extinction, stellar crowding, field contamination. I have to take into account everything in order to reduce the errors in the distance estimation, in ages, and total luminosity. So the step that I did in order to obtain a final catalog for each star clusters are basically this one. I first cross-matched the VVV and VVVX with the Gaia and also the two mass with Gaia. I built clean catalog, basically following these three intermediate steps. First one, excluding nearby stars using the volume parallax. After that, I selected stars within a given radius. This given radius basically is depended on two methods: the visual inspection of density diagrams, as you can see in this one, where you can see a clear overdensity here, but also I used the Gaussian kernel density estimates technique. And I used especially the isodensity contours in order to select this radius around this central overdensity. After that, I used the proper motion in order to decontaminate properly the catalog. Once I constructed my final catalog with the most likely members, I estimate the main physical parameters: reddening and extinction, distance modulus, heliocentric and galactocentric distances, ages, metallicities, and total luminosity. I will show the main also discovery as in this case, because this is the first cluster that I discovered in 2020, I think. And we discovered this cluster as clear overdensity, as you can see here, of the red giant stars. And also it's super interesting because we can see a clear overdensity also in the vector proper motion diagram. So following the photometric analysis that I explained you before, I constructed the color magnitude diagram, I fitted the isochronous, and I suggested that this cluster should be with a metallicity of minus 0.7 with an age of 11. And it's interesting because it's a it's a low luminosity cluster, and it is located in this area where this area we can think that there is the Monoceros ring, which is someone say that the Monoceros ring is an accretion of a dwarf galaxy. Some others think that the Monoceros ring is like a wrap of the disk. So we don't know if this cluster may be an accreted object or not. We need the spectroscopic one. It's hold, I put a question mark here because for two reasons. The first one, because we have another group studied this cluster, Bulge et al. 2023, I think. They got spectroscopic data, and they suggested that this cluster is much more metal rich, something like minus 0.5. And it's younger with an age of 4 or 5 giga-year. Also, it's interesting because Garro 01, which is here, is very close to another cluster that I found, which is Garro 03. And from the analysis, basically, I suggest that Garro 03 is young, with an age of, 3 giga-year, more or less. But again, we have a low luminosity object with an intermediate age. So there are different similarities between Garro 01 and Garro 03. They are very close, few degrees, I think, or minutes, I don't remember, between these two clusters. And again, here we can see the overdensity in the vector proper motion diagram for this cluster.
In physical distance, they are apart one from the other.
You're right, but I don't remember, but some parsecs between these two clusters.
Some parsec or kiloparsecs?
Parsecs, I think. I will check and I will say. I don't remember. These are the actually two candidates, Battiferro 99 and TBJ3. We discarded the TBJ3 as a globular cluster because, as you can see in these images, TBJ3 has an oblate distribution, and also we can see an emission in the mid-infrared. So probably this is a background galaxy. So I discard this between the cluster. About Battiferro 99, I think it's a mess because it's very difficult to decontaminate this cluster. We used two procedure, the statistical decontamination procedure, but also the proper motion decontamination procedure. The proper motion is a little bit better because we can discard these young stars, which are probably in the disk. But I suggest that Patrick 99 is a metal-rich and low luminosity globular cluster located in the bulge with an age of 10 gigayear. The peculiarity of this cluster is the fact that we found some error stars. And with a metallicity of minus 0.2, it's, I don't know, we will see. There is a group of Andrea Kunder that they are searching for error stars in this cluster in order also to confirm the metallicity of this cluster. I also focused my study on the Sagittarius dwarf galaxy. In the Minniti et al. 2021 AMB, Dante discovered several globular cluster candidates, especially in the main body of the Sagittarius dwarf galaxy. I focused mainly on 21 candidates because the other one are very dissoluted and we don't know if they are or not a real cluster. Here there is an example of some color magnitude diagram, but basically the main thing that we derive are, again, the metallicity. We found 17 metal-rich globular clusters, and the other 4 are metal-poor globular cluster. It's interesting because, as we can expect, the metal-poor ones are the older component with the 13 gigayear. But the metal-rich globular clusters span between 7 and 8 gigayear, but also 10 to 14 gigayear. So it's interesting. They are again low luminosity and low mass object. The mass is between 10 to 3 and 10 to 4 solar masses. I constructed the metallicity distribution and the luminosity function for the Sagittarius galaxy, considering also this 21 new cluster. And I compare these two distributions with the known ones. Especially with the Andromeda, the Milky Way, and the Large Magellanic Clouds. The main results that comes from this paper is that probably the Sagittarius progenitor could have been a gas-rich galaxy. This is also in agreement with the Elsenquist et al. 2021 results. Probably many globular clusters survived dynamical processes. Many other dissolved globular clusters associated to the Sagittarius dwarf galaxies probably are real cluster. And finally, since the Sagittarius globular cluster luminosity function peaks at very low luminosity, probably we can conclude that the dynamical processes that destroy globular clusters are more efficient in larger galaxies than in smaller ones, and probably many faint globular clusters are missing in this compilation. Very quickly, I studied other 19 globular cluster candidates in this part of the galaxy, mainly in the bulge one. I want to focus on this one, which show very extreme proper motion, as you can see here. And this cluster is VVV-160. In Minniti 2021, they suggested that this cluster may be associated to the H-read halo stream, but probably not. Very quickly, I want to show mainly these figures just to highlight the fact that it's very difficult to study these clusters because they are embedded in a very crowded field. They are very low luminosity. They are beyond the Vela supernova remnant, so they are a mess. Here there is Patrick 126 that with David are studying now. Here there is another cluster, Garro 02, that I discovered in the same manner as before for the other two clusters, but this time in the Milky Way bulge. As you can see, the color magnitude diagram are always a mess, and also the ages is very difficult to derive a proper good age estimation. In this case, by comparison also with other clusters, I suggest an age of 12 gigayear and a metallicity of -1.3. So maybe this cluster is a fossil relics? We will see. About the spectroscopic one, I want to skip, well, the data reduction. You know how the data reduction can be done. But I used this data basically for getting good radial velocities, and I obtained radial velocity using the cross correlation with a template for two clusters, VVV cell 160 and Patrick 126. And you can see here the mean radial velocity for the two clusters. And using the usual formula, I get the mass. And you can see that the mass of these two clusters are very low, 10 to 3 for Patrick and 10 to 4 for VVV cell 160. I also searched for radial velocity in Gaia, and I get data also for these clusters. I want to skip this other part because I don't have time, but you can trust me that they are more or less good radial velocity, even if the errors are very high, as you can expect. It's interesting, for example, for Patrick 126, there are other three stars which show a similar radial velocity and proper motion of the other ones that I have the spectroscopic data. So it's a good sign that maybe this is a real cluster. And using this software GraphPod 16, I reconstruct the orbits for this cluster for I have radial velocity. And you can see that mainly they show prograde motion, just only one, Patrick 125 show a retrograde motion. And from this, you can see that we can, for example, Patrick 126 show a bulge motion, also Patrick 125, while in this case, Ferrero show Ferrero 54, show a disk motion. It's super interesting. VVV cell 160, which probably is the most eccentric globular cluster candidate. The eccentricity is almost 1. And it's interesting because fall towards the innermost part of the galaxy and goes beyond the sun orbits. So, and for that reason, we can exclude the association with the H-read stream. Here, there are the other cluster. And from here, the main conclusion are that we can at least discern the fact that some clusters are Milky Way bulge halo globular cluster, for example, or disk globular cluster. And depending on the ages that I got, I suggest the open cluster or the globular cluster nature. But again, the ages are very approximative, so we need deeper. I mean, yes, it's super good because the last thing that I want to say is the fact that we increase about 20% the number of the globular cluster if supposing that these clusters are real globular clusters. And the two things that I want to highlight here, that probably if we include these clusters and we reconstruct the luminosity function, we can see the second peak. It's not super robust, we know, because we have few objects, but maybe this is related in comparison with other galaxies, that this cluster may be accreted or survived through disruptions processes. And finally, I compared the metallicity distribution with the Milky Way globular cluster system with field stars. And we can see that something missed. So my question for you, or for who want to help me to understand why, where are the super metal rich globular clusters? I don't know. And yes, basically the main conclusion are the fact that we need to follow this kind of analysis. We can upgrade the metallicity globular cluster system. We can understand if they are real system, and if they are formed in situ or ex situ, and if are the progenitor of past accretions. This is just an highlight for you if you are interested on studentship or fellowship, and thank you very much.
Time for question. Maybe we can switch on the line.
I have one. Grazie. Do you think that are we passing through a new definition of globular clusters, thanks of what is a globular cluster, thanks to these studies, because they are these new systems are usually from what I saw, low mass, low luminosity, in the metal rich part, let's say
Sometimes low age.
low age. So do you think if we are passing through a new definition of what is a globular cluster, because we are
I think
embedded in
that
this classical definition of globular
yes,
cluster?
I think that there is a classical definition between globular clusters and open cluster, but there is not a net definition between, for example, these two classes, because we don't know what about the between exactly. For example, the intermediate ages. For example, if you have 6, 8 gigayear, what is a globular cluster or an open cluster? So I think that in this case we need more information in order to divide these two classes. And also, these are very small clusters. There are few stars in the color magnitude diagram. I don't know if we are losing something, but I don't think so. And probably we can expect, for example, that they were formed 13 gigayears ago, but due to the processes that there are in regions as the bulge, maybe they were disrupted. So maybe the progenitor of these clusters are much bigger and the mass is much more higher, but now we have just these things, small things. So yes, probably the classical definition is just classic and we can move to other definitions. But we will see, I mean, step by
Yes,
step.
it was just a naive curiosity. Emma?
Thank you, Elisa, for your talk. So I have a technical question. So probably you mentioned it already at the beginning of your talk, but what approach did you use to search for a stellar cluster candidate? So did you run like a clustering analysis on the full VVV and Gaia catalog?
Yes, basically I always used the VVV and VVVX survey. And I'm a boomer, so I'm not so good about clustering, thinking, Python, these kind of things. So sometimes I take a tile of the VVV and I start in searching visually. And they are very clear. As you can see, they are super clear. Another approach that I have and I would like to improve in the future is also using the rare stars, because there is a public data that we have, again, from the VVV, that you can see clump of rare stars. And sometimes, for example, for the big globular cluster that we already know, you can see directly that there is an overdensity also of rare stars in this one. But there are also other examples for this small one. So I use what I can do, I can use actually in order to recognize these kind of overdensities. But yes, there are many clustering, machine learning thing. For example, for the open cluster, they found many of them with this technique. But again, you have to go there in order to see if these overdensity are real or not.
And possibly, so possibly a related question. So once you detect a six-star cluster candidate, what will eventually make it for you a real cluster instead of something else?
And the first thing that I use are the proper motion, because sometimes you can see the distribution of the proper motion, which is clear the field, and a blob semi-detached. So this is this can help a lot. Or for example, for the first cluster, you can see a clear overdensity. So I start the photometric analysis that I explained you before, and sometimes you can reach something. In other cases, you can see that they are not a real cluster, or maybe yes, but no, you cannot say more. Especially there was one time that I focused on the few degrees from the center of the Milky Way. I don't know, 3-5 degrees. And it's impossible to get a good color magnitude diagram because the reddening destroys everything. You cannot understand.
Mario, and then last one, Michele.
I have a question actually similar to Daniel's one. I mean, take for example the case of Garro 3, one of the first one you mentioned. I mean, it's a low luminosity, low density, low mass cluster, possibly with an intermediate age. How do you be so sure it's actually a low cluster, not massive open cluster?
I think that the main thing is to get chemical information.
Yeah. So my following question is,
Yes.
You're using intermediate resolution spectra, if I remember correctly.
No, the data that I have are for 3 clusters, and I used iGreens. The resolution is 45,000, so it's
you're
not so
able
bad.
to, yeah, okay. You're able to measure, I mean, either not iron, but also light element abundances.
For these other 3 clusters, yes, I'm working this. For example, this is something that we are doing now with Davide and also Alessio. And for example, for Patrick 126, I have, for example, just 4 stars, but it's a low statistic, but we can understand something more. For another cluster, which is the VSL 160, I have 12 stars, so we can understand a little bit more, we can trust. And yes, I have alpha elements, some iron peak elements, so we can.
Have you found any evidence of like element abundance variation? The statistic looks very, very small. But
Yes, if we want to trust about, for example, for cluster, yes, there are indications that they can say something more.
that would be a way to see if you know an open cluster like structure or the group.
You
Genuinely global cluster.
you have to wait. Stay tuned. But yes, we can understand more about the nature of these clusters.
Last question, Michele.
Just 2 short comments, I hope short. First is that I agree that the distinction between globular cluster and open cluster is somehow blurry. Still, you have to take one or none. Because if you take none, then you have to add 10,000 open cluster from M41 when you compare with your because I see two peaks in the luminosity function. I say, okay, one peak is globular cluster and one peak is open cluster. So you have to take, if you want to play this game, you have to assume a clear definition of what is an open cluster and what is a globular cluster, or no definition at all, and then compare with the entire world of star clusters.
With the entire world, it's complicated because
I know
when
that
there
it's
is
complicated, but easy
Exactly.
things don't
Exactly,
go
exactly.
much far away.
But when I show, for example, my results in the paper, I start with my definition. And for example, depending on super young age, I don't know, for example, 3 giga a year, I could suggest an open cluster. Or for example, if I get orbits of like this motion.
I get it, but then you
eh,
have to take a choice.
Yes.
And move on, because otherwise we are still, okay, we don't know.
But I think
Not much.
exactly, but I think that we can do this after that we have also the spectroscopic point of view. So you can join everything and maybe after that, because at this level, also the age are very approximative. So
Yes, so we are
with
looking
people-
into faint star clusters, and we don't know what kind of cluster are.
also,
Right,
yeah.
okay, I renounce to the second.
Okay, thank you, Lisa, again.